That's our promised land over here. So let's take a look at the next model that we can use, which is called a full wave rectifier. Okay, so how does a full wave rectifier work? Remember, I want to convert my AC into a DC signal. That's the goal here. So this is a full wave rectifier. Same thing, to kind of use a very easy model, we're going to use this ideal diode model to work with here. Okay, so same thing, this is the input voltage over here. And let's take a look at how this fella works. So during the positive half, when the current wants to come here, at this point, remember, I have a diode that is reverse bias. So no current will flow here. Instead, it will go towards the diode which is forward bias. So forward bias comes through here. At this point, this fella is reverse bias, so no current flows through here. Instead, it will come here through your load, here, and over here. Now it wants to go back, so it won't go through there, it will come through here. Remember, it wants to go back here, so it won't go through here, it will go through here. So where was I? Yeah, so follow the green line through here, up. At this point in time, it takes the shortest path back. Okay, so I'll have a very nice positive graph as well. Now, what about when it goes in the reverse direction? Okay, so remember, now is the reverse, the negative phase. Previously it was going up, now it's going down. And over here, it will go through this forward bias. Remember, this diode was placed in this direction. Okay, it was placed in this direction. So being placed in this direction, no current will flow here because it is reverse bias. It can't go through. So it goes through here. Okay, so let's follow the green line. Goes through here, goes through here, goes through here. At this point, at this junction, I have my diode placed like so, and it is reverse bias here. So no current flows through here. Instead, the current will go down. And you'll notice something, that the direction of the current flowing through the load is the same direction as the positive phase. Okay, it's the same direction as the positive phase. So that's very important. If it's the same direction, means it is also going to give me a positive output over here. Okay, so let's follow the green line, follow the green line. Over here, it wants to take the shortest route back here. Remember, there's one more diode here that is forward bias in this direction. Okay, so what we have is originally a AC signal, and because of this full wave rectifier arrangement, I will have positive, and the negative has been flipped up. Remember here, the negative has been flipped up into a positive phase. So we get a very nice, well, take my words back, it's not very nice, but a passable AC into a DC signal here. Okay, but this is of course taking into account the ideal diode. We have not taken into account the voltage drop across each diode if we apply the simplified diode model. So let's take a look at a simplified diode model. Remember, working is still the same. Current comes through here, here, but over here, there's going to be a voltage drop of 0.7 volts. Okay, so current comes here, current comes here, current comes here, current comes here, current comes here. Oops, passing through another diode means there's going to be another voltage drop of 0.7 volts. So in one pass alone, it needs to go through 0.7, another 0.7. So therefore, it's not just 0.7 that we have to take note of here. We have to take note that this circuit will only work if there is a minimum of 1.4. 1.4 because it goes through two simplified diodes. Okay, so anything below 1.4, anything below or above negative 1.4 will not have any signal because effectively no current will flow. So if I draw a line across these two 1.4 values, nothing in between these two 1.4 signals will work. So therefore, anything in between the 1.4 signals will be considered 0. Okay, so hopefully if I've kind of explained how a half wave and a full wave rectifier works. So remember, the goal is to change this in AC into a DC. So what we've done is we have changed it into a DC. Okay. There are two ways to go about it. This is the full wave, and this is the half wave. Okay. And we also have to consider whether we are using a ideal or a practical, sorry, not practical, simplified diode model. Okay, so two things to consider when we want to change AC into DC. So I'm going to leave you to do this now. I'm going to leave you to do this now. Come back, pause the video here, do it, and come back when you have done it. Okay. Okay, so let me go through the answers. Draw the circuit diagrams. I'm not going to draw it. First one, the answer is here. So this is your full wave rectifier, and this is your half wave rectifier over here. Okay, so you should be able to draw, remember, and know how to draw the two circuits. So I'm going to show you the answer for this one. Draw the output waveform of a full wave rectifier when a sine wave of peak voltage 8 volts is used as the input. Use a simplified diode model. So what I have to do here, I unfortunately don't have a ruler to use. So what I have going on here is, let's draw the input signal. Okay, the input signal is going to be a AC signal of 8 volts and minus 8 volts here. Okay, so this is my V over here. And then I want to see what my output is going to be like. Okay, so this is my output, same thing V, right? And this is your time. All right. And so let me change a different color. Yeah, maybe let's use a nice dark blue. Okay, so since this is a full wave and a ideal simplified diode, I have to take into account that nothing below 1.4 volts works and nothing above negative 1.4 volt works. So I'm going to draw my working line here and tell myself that anything below here is going to be 0. So I'm going to start with 0 here, and anything here and anything here will be 0. So this will be 0. So I'm only going to have this portion here. Okay, and over here, nothing works here and nothing works here. So I'm only going to have a signal here. Nothing works here. Nothing works here in between these two. Nothing works here. And I'm going to have a signal here. Okay, now the output is not going to be 8 volts. The output is going to be 8 minus 1.4 volts. So take note of this. I don't think I told you this previously. if you notice, if I start off with 5 volts here, after dropping 1.4 volts, my output signal will not be 5, it will be 3.6. And this comes about because 5 volts, I have to remove away the first knee voltage and the second knee voltage. Okay, so this gives me 3.6 volts. So same thing, I will not end up with an output of 8 volts. It will be 6.6 volts here. Okay. Okay, so I hope you have fully understood how to convert an AC into a DC signal. And there are two ways that we can do so. One is using a full wave rectifier, and the other is a half wave rectifier. Also take into account, okay, where was I? Yes, okay, so I was talking about a quick summary of this. So there are two ways that I can convert an AC to a DC. Yeah, one is by half wave rectifier, the other is by full wave rectifier, and I also have to consider whether it is a ideal or a simplified diode model. Okay, so till next time when I talk to you about what light emitting diodes are, go back through this video, kind of read through your notes and get a full understanding of how we convert AC to DC. Okay, till then, see you.